So I'm actually going to start by doing a little derivation. So we talked about dipoles last time, so let's just review that. We said that dipoles are 2-point charges, one positive, one negative, equal magnitudes, opposite sign. And we worked out qualitatively what the direction of the electric field would be at various locations due to each charge, and then use superposition principle, the idea of adding electric fields together to get a net electric field, to find out the net electric field direction. We found that, for example, on over here, we said that we had an electric field due to the positive charge pointing this way, away from the positive charge, an electric field due to the negative charge pointing towards the negative charge. And then when you do superposition and add those two together, because the positive is closer, you get an E net in this direction. Similarly, over here, you get an E net in the same direction because we're closer to the negative on this side. You can do the same on the axis, or on the perpendicular axis, rather, and look at the electric field due to the positive charge, the electric field due to the negative charge. And then from the symmetry of the situation, you can see that the y components are going to cancel out, and you get a net electric field that's pointing not toward either charges, but kind of perpendicular to that axis and in the opposite direction from this one. And so we saw this program I think we showed last time, where we can go around a series of observation locations, kind of in a circle surrounding our dipole, and see this sort of pattern of electric field where it's pointing one way, and then as we move from the axis to the perpendicular, it kind of curls around and starts pointing in the opposite direction, and then kind of starts to curl back again. So this is a pattern of an electric dipole, the electric field of an electric dipole at various observation locations in space, and it's not just in a plane; it's everywhere in space. We could do this elsewhere, but this is just one plane to show this in. So what I want to do is go through a derivation, a couple derivations. And these derivations are in the textbook, so I'm not sure if you should just start copying down notes it's because everything I'm going to do here is laid out in the book. So it might be just more useful to just kind of follow along and and not have to slavishly copy every single line. But we can work out an expression for the electric field of a dipole at various observation locations by applying the superposition principle and just doing a little algebra. So let's say we want to calculate a general expression for the electric field of a dipole at this particular observation location on the axis. So let's say that we have a negative charge minus q here, positive plus q here. We'll say that the distance between the two dipoles, we'll call that S. And so the position of the negative charge would be negative S over 2, 0, 0. The position of the positive charge would be positive S over 2, 0, 0. And then the observation location, which I'll just call A, is a distance D, just call it D, from the center of the coordinate system, from the origin of the coordinate system, which is right in between the two charges. So let's call that D, 0, 0. And I'm going to go through the superposition principle, find the electric field due to the positive charge, an expression for that, an electric field due to the negative charge, and then add them together. Okay, so let's start by finding the electric field of the positive charge. Well, superposition says we can just treat it like a point charge and ignore the other point charge. So we're going to use our field due to a point charge, which is 1 over 4 pi epsilon 0 q of r squared times r hat. I need to find the r vector, and I'll call it r plus to indicate it's the r vector pointing from the positive charge. That is final minus initial, right? So it's going to be the observation location, D, 0, 0, minus the source charge location, which is S over 2, 0, 0. And so we have R plus is d minus s over 2, 0, 0. We can then find the magnitude of this thing, and that since it only has an x component, the magnitude is just going to be d minus s over 2, right? So we have d minus s over 2 for our magnitude. And then, of course, then the unit vector, which we could just get by eyeballing this, but the unit vector is going to be what? 1, 0, 0, right? So now we can calculate the electric field. We have E plus then is 1 over 4 pi epsilon 0 Q over d minus s over 2 quantity squared, okay, times the unit vector 1, 0, 0. We can do the same thing for the electric field due to the negative charge, right? Similar situation, we have R minus is D 0, 0, same observation location, minus A minus S over 2, 0, 0. So the vector is D plus S over 2, 0, 0. The magnitude is then D plus S over 2. And again, the unit vector is still 1, 0, 0. It's still pointing in the positive x direction from the negative charge to location A. So we get here for our electric field due to the negative charge, 1 over 4 pi epsilon 0. I have a negative Q now, taking the sign of the charge into account. I'm dividing by this different magnitude, d plus s over 2, quantity squared, times 1, 0, 0. Okay? And so if I use superposition, I can add these two vector expressions together, right? And so if I say E net is E plus E minus. What do I have? I have the only component I'm going to have is an x component, right? So we saw qualitatively that the net field is pointing in the positive x direction. I have the same. I have some things I'm going to factor out. The 1 over 4 pi epsilon 0 is the same for both, and there's a factor of q here, although there's a negative sign here I got to be a little bit careful about. So I'm going to have a 1 over 4 pi epsilon 0. I'm going to have a factor of q. And then I'm going to have 1 over d minus s over 2 squared. I'm left over with a negative sign here, so this is minus 1 over d plus s over 2 squared. And that's it for the x component, right? It's going to be in the direction 1, 0, 0. Or I could write this as the x component, comma 0, comma 0. Okay, just multiply that through. Well, that's kind of a long, messy expression. So I'm going to do a little bit of simplification, and then I'm going to make an approximation. And the approximation we want to make is this. Typically, when we're dealing with dipoles, we're dealing with situations where the observation location is a lot farther away, or the distance to the observation location is a lot larger than the separation of the two charges, okay? And if you think about dipoles in nature, such as permanent dipoles of molecules like water molecules or hydrogen chloride molecules or what have you, you have a separation of charge that's really tiny, right? That's on the atomic scale, but you might be looking at several nanometers, even at the nanoscale. Nanometers is a lot larger than the separation of the charge. So typically we're going to deal with situations where the distance is a lot larger than the separation. Okay. So let me see if I can simplify this a little bit and then take that into account. Well, I'm going to need to have I want to add these two fractions. So I'm going to need a common denominator, which means I'm going to have to multiply top and bottom by d plus s over 2 squared. I'll still have this here. I have d plus s over 2 squared minus, and I'm multiplying top and bottom, d minus s over 2 squared on the other side, or on the other fraction. And then I have d plus s over 2 squared times d minus s over 2 squared, comma 0, comma 0. And then the algebra just gets kind of messy. You would have to expand this out, and I'll just write out the expanded expressions. We're going to have d squared plus ds plus s over 2 squared, just doing the square here, expanding the polynomial. And then minus d squared minus ds plus s over 2 squared, that quantity. And if I bring that negative sign through, I'll have a negative here, I'll have a positive here, and I'll have a negative here. Okay? All divided by d plus s over 2 squared times d minus s over 2 squared. And then this is, again, a vector expression, so this is comma 0, comma 0. I'm kind of running out of room there. Well, a lot of terms will drop out in the numerator, right? We have a d squared canceling a d squared here. We have a ds adding together, so we get a factor of 2. And we have s over 2 squared canceling with minus s over 2 squared. So we end up with 1 over 4 pi epsilon 0 q times 2 ds over d plus s over 2 squared, d minus s over 2 squared. Okay. And now we can think about making the approximation. Okay, if I look at the denominator, if I'm saying that the distance d is a lot bigger than s, then when I add d to s over 2, I get approximately just what? Just d, right? If I subtract s over 2 from d, I'm going to get approximately just d. Okay, so the denominator will boil down to what approximately? Not 2d squared. We're going to have d squared. We have a d squared here, but then another d squared. So right, so we're going to get d to the 4th. Okay, so this comes down to 1 over 4 pi epsilon 0 q times 2 ds over d to the 4th, and then a factor of d cancels top and bottom. So we end up with 1 over 4 pi epsilon 0 2, right again, q times 2 times d, times s, 2 times s over d to the 3rd, 0, 0. Okay, so let me rewrite just the final result. What we just found is the magnitude of the electric field, net electric field of a dipole at a location on the, what I'm going to call the dipole axis, meaning the axis that runs through the two charges, okay? And that magnitude works out to be 1 over 4 pi epsilon 0 2 times q times s over d cubed. And again, the approximation is that d is much, much bigger than s, okay? And in fact, just in terms of the symbols here, we often just replace this with r. We just, instead of calling this d, we just call it r, just to indicate the distance away from the dipole, just as was commonly used. So you'll see this as 1 over 4 pi epsilon 0, 2 qs divided by r cubed. And again, the approximation being that r is a lot bigger than s. And this is a nice, we don't have to memorize this formula, but it's a nice formula to keep in mind because it gives us some useful information. First of all, we have a nice concise expression to just give us the electric field. We don't have to go through the entire superposition principle again. Notice the difference in the distance dependence. It's 1 over the distance cubed rather than 1 over the distance squared like in a point charge. So that means if I calculate the electric field, or I measure the electric field due to a dipole, and I double the distance, I measure it somewhere else on that same axis twice as far away, the field goes down by what? By a factor of 8, right? By a factor of 8, okay? So it's dropping off more rapidly with distance than a single, the field of a single charge, okay? It only applies, though, for on the dipole axis. I specifically said that this location was on the axis. It's not a general formula for everywhere in space. We could derive one more formula, and I'll go through it now. That's useful to keep in mind. I'm going to pick a different location, call this location B. And B is going to be at location 0D0, okay? So this is on what we're going to call the perpendicular axis, perpendicular to the dipole, okay? We can go through the exact same steps again. So let's just go through it, go through the derivation. I'll just kind of overwrite what we had. Same steps. We're going to have R plus being 0D0 minus S over 2, 0, 0. So our new R vector for the positive charge, remember the R vector points from the positive charge to the observation location. So that's going to be minus S over 2 D0, okay? Which we can check. Notice that it has a negative x component and a positive y component, right, for that vector. So that seems to make sense. The magnitude is not going to be d minus s over 2. What's the magnitude going to be? How do we calculate the magnitude? Square root of sum of the squares, right? So it's going to be square root of s over 2 squared plus d squared, okay? So r hat is not going to be 1, 0, 0 in this case. We need to actually evaluate r hat. R hat's going to be negative s over 2 d0 divided by square root of s over 2 squared plus d squared. Okay. Put it all together and calculate the electric field of the positive charge alone. We have 1 over 4 pi epsilon 0 positive q divided by the magnitude of r squared. So the magnitude of squared is going to be s over 2 squared plus d squared. Multiplied by the unit vector, negative s over 2 d0 times the square root of s over 2 squared plus d squared. I have s over 2 plus d squared here, and yet another factor of s over 2 squared plus d squared to the 1/2 here. So I can multiply those two together, right? And I get what? That expression raised to what power? The 3/2, right? So let me rewrite that. Some more room here. 1 over 4 pi epsilon 0 q over quantity s over 2 squared plus d squared to the 3/2 times this vector negative s over 2 d0. Okay, and I'm going to leave it like that for right now. Let's get a little more room and do the electric field due to the negative charge. Before we do that, let's just check it again. Notice that this expression out in front of the vector is all positive numbered. This is the positive charge. Magnitude's positive. The electric field has a negative x component, positive y component, 0. The electric field due to the positive alone. Okay, and that's what we would expect. E of the positive charge should be pointing away from that positive, has a negative x, positive y component. Okay? Questions? Okay, same thing for the negative the electric field to the negative charge. We have R minus equal to the observation location, 0d0, minus the source location, which is now negative s over 2, 0, 0. So R minus is 0 minus a minus gives us a positive s over 2, d 0. So the R minus vector has a positive x and a positive y component. That's R minus. The magnitude of R minus is square root of s over 2 squared plus d squared. Same as it was before, right? Same as it was for R plus. And then we can write R hat, which is positive s over 2 d 0 over this square root. Okay? Put it all together. The electric field due to the negative charge is 1 over 4 pi epsilon 0 times a negative q. Okay, it's the negative charge divided by the magnitude squared. So we have s over 2 squared plus d squared times the unit vector. Once again, we can simplify this. We have this. We can get this factor to the 3 halves down in the denominator. To the 3 halves times a vector s over 2 d 0. And let me just bring the negative sign on the charge inside the vector. So we'll have this as positive q, negative s over 2, and negative d for our x and y components. Okay. Check the direction. We have a positive scalar out front multiplying a negative x component and a negative y component. The electric field points in the negative x direction and negative y direction, right down like that towards the charge. So it seems to be okay. Okay. When I add the two vectors together, I have the same scalar multiplying the outside of these two vectors, right? So I can bring that outside. Let's just do that. 1 over 4 pi epsilon 0 q over s over 2 squared plus d squared to the 3 halves. And then I just have to add the two vectors, negative s over 2 d0 and negative s over 2 negative d0. And what do I get? The x component, when I add those two vectors together, I get what? Just adding that component and that component. It's a little hard to see, but this is a negative s over 2, so this should be negative s. The y component is 0, and the z component is 0. Okay? So let's bring that s outside, and then this will become a little bit more clear. We have q times s over 2 squared plus d squared to the 3 halves times the unit vector, which is just giving the direction. It's pointing in the negative x direction, which is what we expect. It's what we said last time. So we're ending up with an E net pointing in that direction. Okay, so that seems to work. So out front then is giving us the magnitude information. And finally, the last step is applying the approximation. D, again, we're assuming is much, much greater than S. If D is much, much greater than S, what do I get down in the denominator? D cubed, right? Did everybody see that? d squared plus s over 2 squared is approximately just d squared if s is really small, so that essentially goes away. D squared to the 3/2 gives me d cubed. So I get 1 over 4 pi epsilon 0 qs over d cubed times negative 1, 0, 0. Okay? So let's write our other result then. This was the magnitude of the electric field of a dipole on the axis. And if I can erase this, I'll just write the magnitude of the electric field of a dipole on the perpendicular axis, this perpendicular bisector, right? It would apply anywhere along this axis. And that is 1 over 4 pi epsilon 0, similar looking expression, except that there's no factor of 2 here. It's just qs over d cubed, or if again I just make the substitution, call it r, we can just call it r cubed. So again, this is the approximation when r is much bigger than s. Okay? Okay? So formulas that you don't have to memorize, but you should be familiar with the way dipoles behave, and you might want to just keep in mind that dipoles depend on 1 over the distance cubed. They depend on the charge and the charge separation. In fact, this quantity, Q times S, we often group those two things together and give it a name. This is called the electric dipole moment. And the symbol that's used is often lowercase p, which is a little unfortunate because it's the same symbol as momentum, but we have to live with it. P is equal to Q times S. Okay? So why define this P thing? Well, for microscopic dipoles like molecules, it's often easy experimentally to measure directly the dipole moment. You might not know the individual charge on each side of the dipole. You might not know how far they're separated. In fact, it's sort of for microscopic dipoles, it's more of a continuous separation rather than 2 points being separated. But you can measure the electric dipole moment. And so certain molecules may have a permanent value of the electric dipole moment. Okay, so it's a good quantity to keep in mind. It's actually a vector. And it points from negative to positive, isn't it? I'm confused. Don't quote me on that. Check the book. Okay, but there is a vector direction to it, and I think it might even be different for chemistry versus physics. I think physicists I think say it's from the negative to the positive, and chemists might say the opposite. It's in the book, so double check it. The direction, notice that these are just formulas for the magnitude. Okay, we're not giving direction information here as we were with the electric field of a point charge, because you have to, it's going to change. It's going to change depending on whether you're on the axis or on the perpendicular. The direction you should just be able to work out for yourself. Okay, we went through qualitatively how to determine the direction last time by looking at the electric field of each individual charge and applying superposition. So if you're asked to write a vector expression, you might not be able to pull that out from the formula. You actually need to draw a picture, draw the electric fields due to each charge, and work out what the direction is, and then figure out what the components have to be. And we'll be doing that a lot over and over again in this course. Okay, the directions is something that you need to work out often from physical situations, from the geometry of the problem, rather than just plugging into a formula and getting the numbers. Okay. Yes. This magnitude would be the same as if it were on the z-axis. That's correct, because the z-axis is also perpendicular to the dipole, right? And it's one reason why I didn't label them x, y, and z is because, it's going to vary depending on the orientation of the dipole, right? If I have a situation where my dipole is lined up like this, then this is now the perpendicular axis, right? And so I'd have to use that second formula along here and the first one along here, okay? So be sure to go by the orientation of the dipole and not by just x, y, or z.